Okay, we're back. So this is something that I'm trying to get better at as a professor who does stream, but whether you noticed or not, and whether you're watching this video for the first time, I showed some stuff that I was like, I don't really feel comfortable about that being out there for long term. So what I did is I stopped the stream, restarted the stream, and then deleted that video, so that way it doesn't exist anymore, at least in a space that people can access it. But anyways, I was kind of showing again how I'm developing some of these, so you're going to see at least one more of these. But now, let's see. Day 11 key should be done, ready to go. Can I duplicate this one? Ooh, new quizzes you can duplicate. Cool. Oh, I wish classic quizzes had that. That's going to save me a little bit of time. And let's make it due. Oh, it didn't save the due date, though. Dang. Alright, not as good as I was hoping, but it does save some settings, which is nice. And it should save some questions, which is nice. Great. It does. So here, this works again, but I want to edit this because I need to check the responses and change to the new code. Okay, that's done. Got the key for that figured out. So, okay, now I don't need this due, though. I don't really need a due date. That's why I bet it would have saved. Let's just not have one, then. Okay, now students have access to 9, 10, 11, 12. 9, 10, 11, 12. Those keys are available. They have everything they need for the midterm. I'll get going week 3 soon, but I'm pretty happy with... They have their peer review stuff, which is due the right day. Yeah, great. Those will unlock peer reviewing at the proper time. No attempt has weeks 1 and 2. This has week 3 keys ready to go. I have moved those ones out of the way. This as well, I kind of want to move down and out. This I want to move out of their way. Again, I'm assuming this shows to them. I don't know if it does. Midterms are really not important, so let's leave those at the bottom too. Week 3 QPTs are pretty important. Surveys are pretty important, but this is more important. Keys are pretty important to students. Contract details are pretty important to students, and then these are super important. Heck, this is the most important one. Is it? It is a little important to students. Let's rate these by their scores. Proctor U is very important. Or at least some representation that it is. This is important in week 3 and keeps it there. Keys are pretty important too. But anyways, I'm pretty happy with this. So, okay, this is all done. Week 3 keys are done, so let's check off our list. And let's mute this. And let's go to checklist. And now we're going to be, so current content is teaching stuff. Or we'll make it better than that. Let's say Tuesday prep class. That's what we're moving to. So to prep for this class, I want to think a little bit about how do I want to approach this class, and as well, go to my schedule, go to my home, join class, link, and then this is our class. So every class I have a folder for that day. So this is going to be tomorrow. So let's make a new folder. We'll name it 7/15. And in some ways, this is midterm 2 review, isn't it? Yeah, because this is the class before the midterm 2! Gosh! Man, this is the only reason I'm not like... Or this is the only reason I'm a little like stressed... What should I say? Stressed out? Yeah, I am. Or not stressed out, but the only reason I'm not a huge fan of these super tight online courses is I don't really get a lot of time to teach a subject, or maybe I'm not teaching a subject, but tutor a subject. Right? If I have this flipped classroom where a lot of the content, the lecture, is provided by another professor, and so when I come in, I'm trying to give my take on things, my connecting back to classes you've been in before, my things that I think are important, how my class works, things that people should care about. But anyway, so it's going to be another midterm 2 day. So let's create that for a second, and then a little carefully, I want to just move some stuff around. Just really quick, so something I want to show you. I blacked out all my student names for this, but what students do is in class, to get part of points for your class, they're updating a sheet in live time where it's like, okay, I asked a question in chat, I did notes, I had my mic and my camera on, my class quiz I did, I even asked Professor Pratt, or I answered a student question with my mic, and so it sums how much you've done in the class that I can use to help their scores later on, and then I do some funky stuff later on. That's what these are. So for now I can get rid of this, but right, this is what students see, and I'm going to add to this once I release this folder. Well, actually, it might already be released, which is fine, but students will come in here and they'll find their name and they'll start figuring out, but because this is a new day, I get rid of all the points that were earned last time people were in class, and I make this now my new class day, and oops, that one should also be deleted. Great. And let's even just say get rid of that. Alright, doesn't matter. So, but this is something that students do, and then I can't open the other one, but I have some quiz records. But what I do want to show is, let's add a Google slide, create and share. And so what I have in here is 7:15. Student notes. How does it feel? And so this will be student name, or let's say maybe note owner name, because it has to be. I have a TA who has to check if they're actually doing the work. So there needs to be some ability to search this. So that's what this textbook is for. But then all I do is just make enough slides for, theoretically, if every student did it, it's about 60. So that's done. Then I go in here and do a new one. New slide, and then I don't know what this will be yet, but this is going to be the 7:15 student quiz. Attempt and peer review I could add to this as well. And then let's be a touch careful before I show something. Hello, we have a student. Hey, Professor Pratt, I'm going to post a discussion too, but I have a quick question regarding an old problem I didn't figure out. I emailed it to you, but which pathway would be better? Of course, once you're done with this. So I would say, for now, post it to, If it's a previous problem, let me think about it. Well, let's just do it now. If you send it to me in email, let me up or look at it for a second on stream, and we can talk about it. So go to email, and I'll make a timestamp for this. So we have a student question now. So again, let's even show this anything. No, everything's looking good. Great. So basically, what's going on is over here. I'm going to say at about 11 minutes. Student question on, let's see what it is, and we'll update our timestamp in a second. So, okay, I see the email. Which pathway would be correct for the problem to form the hydrate? The YouTube video showed the red one, but I thought the yellow one makes more sense. Ooh, interesting. I'm very excited. So, let's make sure there's no student name on the Okay, so I'm going to change this to 12 minutes. So I'm basically saving a timestamp for the question so students can see that, move that out of the way. We'll come back to this later. But right off the bat, I think my student who emailed me is correct, and the student here kind of debating this thing with me. I do feel like the yellow pathway is the one that makes the most sense, because it seems to me that what we have in this discussion is we are creating cations. We're creating things that are acidic in our solution. And yes, there is anions in this situation. When we attack the carbonyl, what I would like to say is this. I think there's a missing step already too, and some things about this mechanism we might want to talk about, how we maybe get a little bit, I want to avoid saying lazy, because that's not the right terminology to express my thanks for somebody who helped me so much. But with these carbonyls, I really think we should always have, so example, my first thing I want to comment about this student email is I think you want to activate this carbonyl like we showed in class 1, and then we kind of lost it a little bit in some other classes I noticed, but I want to actually pre-activate this carbonyl. I want to show an acid donating an H+ to this carbonyl first, so that way when we do open it, we are bringing, this does not appear, this anion here, let me get rid of some stuff here, so I'm a little bit more clear. I think we want to, ahead of time, take this, find some acid, leave water behind, and then have a step in between here where we have a carbonyl that is activated, so now water does want to come in. I'm sorry for how bad this handwriting is. I'm trying to draw the intermediate step where we have a protonated carbonyl that now when we come in, we don't have this anion, but instead we have a neutral alcohol created, and then we have this acidic compound here that we can do a deprotonation step. I would even say, yeah, we do need to do probably a deprotonation step, because the next thing we're going to do is form because there is some more missing steps here where we're going to form a carbonyl again. But this answers the student's question. It's actually neither the yellow path nor the red path. I would say don't do either of these necessarily, but instead pre-protonate your carbonyl. Use an acid in the first step to protonate your carbonyl, so when you add to it, you don't need to do the steps that you put over here. Instead, go right into the deprotonating, so now we can form the carbonyl again. Or not. Let me think a second. Boom, boom. Boom, boom. Yes, I'm okay with this. Yeah, that's what I would recommend. I guess what I'll email back to this student is say, yep, we answered this on the live stream where I said, I think neither yellow nor red pathway, what they suggest here, but because I want to make sure our mechanisms are consistent with the medium we're in, which typically, when we're making acetals, we typically do them in acidic conditions. When we use a base, we tend to start reacting with the alpha position of our carbonyls, especially if they're not electronegative, or they're not esters, they're not amides. And so that's kind of my answer, is that I don't think it's either of these pathways you suggested. I think it's probably best practice to protonate your carbonyl first so you don't run into this problem. Then when you form the acetal that you see here, you're good to go. I might be using some words wrong. I wonder if an acetyl can be an OH. But anyways, that's my thought. What I'm going to email back to this student and even say in chat here, because I think they're here, is I did notice that there was a little bit of loss, and we seem to go back to using basic conditions sometimes to make some of the acetals, which felt a little bit like it wasn't following what we said in class 1. And so again, I'm not going to grade super harshly on these things on the exam, or at least I'm going to try to design questions that take it more step by step and I make it clear what the step is that I want to do or I want to interrogate. But does that answer your question, student? That I think if you did have to choose a pathway, I agree with you that I would almost to some ways have to do the yellow pathway, but even then, I don't like this entire thing in general because you have anions and cations appearing in the same mechanism, which is allowed. We see it in other mechanisms, and what we're teaching you in the first week of classes or up to the first midterm is that the creation of these compounds is typically done under acidic conditions. So I don't really ever want to see an anion. I want to see only neutral compounds or charged compounds. In this case, the way to do that is to follow the steps that I'll kind of circle in green here. Instead of going right to the attack that we see here, like this step shows just the attack, do this arrow here, protonate your carbonyl. Because if you protonate your carbonyl ahead of time, you have a positive carbonyl that then you attack with water, making a neutral alcohol, and now your protonated water that attack needs to get deprotonated to make the product that we see circled in red below and then recircled or pointed to with an arrow in purple. So, yeah, again, we get confused sometimes as teachers, sometimes to forget to do certain things. So no shade being thrown, but I believe that's the proper way to approach this kind of situation, especially in acid. Okay, I just sent you an email back, student, so you now know that I don't think it's either yellow or red. I think you do a step ahead of time to avoid the yellow-red question in general. And back to some other stuff. So let's do... So, back to kind of how I prep my classes. Again, this quiz is kind of the starting page for the quiz that the student will look at, and I need to edit this or whatever. So I'll do a new question here after I think about what would be a good one for them to do. And what's really important to me is, well, first we need to remove that link because we'll have to add that later. It's important to me in these quizzes that students do that they're interacting with each other because, yeah, taking a quiz by yourself, answering a question is great, but if you can produce an answer that you specifically make wrong and then have students look for something that's wrong, it creates kind of in my opinion, it creates a kind of a fun environment of feedback where you have to give feedback on something. They think they put something in there that's wrong, but in addition, if they put other things that wrong and you're like, there's 3 things that might be wrong here in my opinion, they're teaching the student in real time if they're comfortable with the material and they can look for more things that are a problem. Anyway, so that's kind of what I do is my quizzes are always going to involve some sort of feedback loop and some sort of different question than a typical quiz where it's not you always proposing the right answer, it's sometimes proposing the wrong answer or having a part of your answer be specifically wrong is a more creative way to approach some of this material to see how deeply you're understanding it. So anyways, that's going on. And eventually, let me actually do something else quick. And really, I should make one of these at some point that's like already ready to go. But for now, I'm doing what I shouldn't do, which is a bad process that I keep doing the bad process. But I'll fix it later. So and then again, assuming lots of students take this test, there could be 60 of them, so we'll just make a bunch of them. No way is everybody going to do it, but we've got that going on, and I'm going to make sure I have it set up so that we have the tracking your progress thing. So I'll do a new question, remind myself to do that. Get rid of that. And let's do this change too, so I'll make sure that's good to go. Okay, so we've got again, a lot of this stuff is a little messy, but it'll get better the more I do it. Gotta have something to start with, so that links to the right thing now, which is great. I'll put it in a new question once I'm ready, and we've got that all set up. So great, 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 great. Get rid of that. Get rid of that. And I should update that a second to a second. And then it's pretty important too that anytime I do this, when I do share it, I make it editable. That's what allows students to actually track stuff. So. So now all these are editable, so now they can do the quiz, they can show their notes, they can show me how they participate in class, they can keep record of their quizzes. And so that's the last thing that I do. Last thing is going to be the PowerPoint, which I create the PowerPoint in a separate document, partially because I like it that I can, basically, it almost looks like I'm making the PowerPoint in real time, and they can't scroll ahead of the PowerPoint, because I want to keep students' attention on what's being talked about right now. They can look backwards, but I don't want them to look forward and lose them. So I'm going to make that PowerPoint elsewhere, and then as I'm teaching, I just copy and paste the slides over as I'm moving through the class. So the thing that's been made in a separate thing that they can't see is being updated in real time as class is happening. So that's what I'm moving on to. Higher and higher. But for now, we can at least create the slide. And I don't know what I want to name it yet, but we've got that going on. So, and because class notes doesn't sound great, and we'll just do 7:15. Okay, so what I'm about to do is watch some Dr. W videos. So I'm going to have to mute my lovely bird sound because I can't. I don't want to. I don't want to share student names from what he was teaching. So, anyways, it's going to get a little boring around here. But anybody who pops in, let me know. And I'm going to make a quick edit here. So this is at, let's say, 30 minutes. And let's mute this. So basically what I'm going to do is watch a video, maybe do like a pop-out thing or whatever, where you can see a little bit visually what's going on and you can see my notes that are happening in real time. It won't be sharing the desktop audio because he says student names at some points in his video, so I'm going to keep the audio just coming to me, not being streamed. But students can kind of almost have like it's not a great watch party, but it's a version of it. So I'm going to get some things set up and then we'll start getting ready for class. Right, so this is the kind of cool reminder that we started with acidic conditions with ketones and aldehydes because acidic conditions with ketones and aldehydes are what allow us to attack the carbonyls carbon. But under basic conditions, you don't attack the carbonyl carbon. You deprotonate the alpha position more often than not. And so that's why we see these aldols. And now this is called a crossed aldol, because we are having a ketone with an ethyl group and a ketone with an isopropyl looking thing. Well, I guess it's still it is a propyl group instead of an ethyl group coming off the ketone on one side. We now have 3 carbons coming off. So we're going to get different products. And something that's kind of interesting about this is all the different products that can come out of this thing. So let's continue to see how this discussion goes. But in class 6, we talk about crossed aldol, and reminder that basic conditions with alds and ketones attack the alpha carbon, not the carbonyl like in acidic conditions. So that's something that I think is super, super important personally to keep an eye on as an important part of this. So, okay, we'll keep moving on. He says this is not a good. He said this is not a good reaction. Brings up the good point that when you do aldol chemistry, if you don't design your starting material with some thought, you're going to create a heck of a lot of products. So be careful. So he just drawed it reacting with itself. The going to the right reacts with the new ketone. Going down reacts with the same ketone. It's a mess, is what he says. He calls it a useless reaction because you make a mess of products. And he's kind of right? In the research world, I've created bad reactions where it sucks purifying a reaction that you didn't think a lot about before setting it up. the more similar the things you are creating, even if there's a couple of carbons different, really hard to get that stuff apart. Impossible, but really hard. It takes all the time in the world. Yeah. The distribution of your products based on stability, kinetics, how you ran your reaction, all sorts of stuff. That's why he calls it not a good reaction. And so he's going to probably bring up some smarter starting material. Or sorry to say smarter, but well-designed starting material. So again, let's just kind of analyze what happened here that's different from what we started above. The first thing is, when I look at the aldehyde has no alpha CHs. Right over to its right, it's an aldehyde, just an H. So there's no CHs there that under basic conditions would turn into an enolate. There is no CH on that side of an aldehyde. By definition, it's an aldehyde. And then the most clever thing, something that I don't know if I hinted at in my exam, I can't remember if I did, but when you have an aromatic group to the left side of your aldehyde or ketone, it's very important to notice that this carbon has 4 bonds to it. A double bond because it's an aromatic ring, a single bond because it's an aromatic ring, and a single bond back to the carbonyl. So this carbon has 4 carbon bonds, 3 carbon bonds. The 4th one is the double bond, but there is no CHs. So the first part of his reaction, the first reactant, is never going to have the base form an enolate. It's never going to be nucleophilic. It has no alpha carbons. And then the beauty of his compound to the right is he shows you in blue the only thing that can become an enolate is the right carbon. The right carbon has a CH at its alpha position. So this is a well-designed cross-aldol. So let's even make a note about this. Well-designed cross-aldol should only have 1 alpha carbon because we avoid the problem above. And so that's what we see here. We only have 1 alpha, I shouldn't say just carbon, I should say alpha CH to mess with, or to have a base attack because we avoid the problem above. Great. And he does go all the way to dehydration. So there's a pretty intense mechanism to get here. But look at that, 99%. Oh, beautiful. And a cute little thing that he probably is going to point out in lecture. Also, he made an NO2 group. An NO2 group does do a good job of pulling electron density out of a ring. So this electron ring is already kind of electron poor, which is then, through induction effects, making the carbonyl more partial positive, which my first question as a student that I would ask is I'd say, whoa, Dr. W., this aromatic ring is pretty electron withdrawn, which makes the carbonyl pretty electron withdrawn. Because we've made the carbonyl electron withdrawn, certainly it's going to work at an aldol, but is it really 99% of this? Or do you sometimes... Oh, no, you wouldn't. Never mind. There is no good leaving group. So we don't even worry about the Chem 202 problem of what if the OH attacks the carbonyl now? Well, if it does, it doesn't go anywhere. It is doing that. I guarantee you it's doing that. But it doesn't go anywhere. It's stuck in this intermediate world of never going to a stable product. It's going through some reaction coordinate diagram, but it never gets to a lower energy state. So we keep pulling it away and back into the product that he showed here. So answer my own question, even though this carbonyl is electron withdrawn, we still don't do carbonyl chemistry like in 202 on it. We don't make tetrahedral intermediates that do anything interesting. Beautiful. Ooh, he is talking about this. Well, why can't my compound on the right react with itself? Well, because we made this one more electron withdrawn. The one on the left we made more electron withdrawn. Just in general, aldehydes are better electrophiles. Because carbon versus hydrogen, if you think about electronegativity. And sterics, as he says it, which maybe is the right way to say it. I've always said sterics. Love his notes here. Intramolecular one? What does he have him do? He's making him do the intramolecular one, so we don't see it yet, so we're going to have to skip ahead until we see it. Bonkers, bonkers, bonkers. Okay, great. So always doing something that anytime you're an anxious student, start putting in electron pairs. Start putting in CHs that are missing. Start labeling things, whether with color or as he's doing with numbers, to figure out what we're going to do. Because we need to think about, once we do intramolecular, the reason a reaction goes a certain way, the reason certain things happen is because we need orbitals to overlap. So I bet he's going to make this argument about 7 and 2 being where the enolate that forms, that does the reaction, is going to form. We're not going to form it on carbons 4 and 5 because the electron or the overlap is not going to be very good. If you form the enolate by deprotonating, and reminder, what is an enolate really quick, as I'm saying that a lot. Right, the enolate, let's see if there's a good... Thank you, Master Organic Chemistry, the legend of the game, right? This is a alpha proton. You deprotonate it, the electrons double bond to carbon, double bond to oxygen, goes up on oxygen. And so this is a cool reactive intermediate that we use to form bonds to the alpha carbon. Rather than the carbonyls carbon being what forms bond, we're forming bonds to the carbon next door. So incredible stuff. That's what all this chemistry is being based on. But what I want to kind of oracleize about or propose he's going to talk about is, first, intramolecular reactions are always faster. Your orbitals, your reactivity, is localized by forcibly connecting it together, and so it clicks together much faster than if you have two things floating through space that aren't connected. The likelihood of them connecting is less than if you force them together and force them to be together. But if they are together, you can't react things that can't get close to each other, like my knuckles, for example, but the things that can overlap, like my pinkies, for example. So he's probably going to talk about how there can be, you will probably have to purify out some products where you formed an enolate and it attacked another molecule, right? If you ran this super concentrated, you're going to run into that problem. I bet the more you dilute this reaction, the more you dilute the ability for it to interact with other compounds, the better you get intramolecular results. Run it super dilute. And this would be a cool quiz question, but I want to be careful coming up with too many clever quiz questions that aren't based in Dr. W's lectures or QTPs, because it's not fair. I haven't talked about it or shown how cool I think it is. But anyways, so if we form this enolate on 4 or 5, it would have to react with another compound, another one of these starting materials. But if it forms on carbon 2 or carbon 7, I bet we're going to have the, if I count, 1, 2, 3, 4, it's going to be a 5-membered ring. I think, right? 1, 2, 3, 4. I think it's going to form a 5-membered ring, which, not the best overlap. I'd ideally put another carbon in between 4 and 5 and extend that ring out to show the 6-membered ring coming back, because that is like the other, just because of humanity loving carbon bonds and our Earth being a very carbon-based world, we tend to like 6-membered rings because they form the 109.5 bond angle. 5-membered rings don't quite get there. But anyway, let's see what he says. So he's labeling all the alpha H's. He's showing us all this alpha CH's. Symmetrical. 2 and 7 are symmetrical. 4 and 5 are symmetrical. He's saying there's 2 enolates because it's symmetrical. Let's keep moving ahead. So he just showed us the 5-membered ring that's happening. Again, I kind of wanted to, I think you could do a 6-membered ring and it might be more, you know, it doesn't matter. It's fine. 5-membered rings are fine. So again, what he did is he redrew, showing the enolate, although I don't love how he showed it. I guess I'm okay with it. I would prefer to see the enolate. I don't like seeing the anion on carbon, but I do like that. He's reminding us the enolate is not active necessarily on the oxygen, it's active on the carbon. And so the enolate can be confusing to students because if we look right over here again, you see the O minus, you can't see because I'm pointing, right? But you see the O minus having the negative, and so you might forget that it's the carbon that's reactive. And so that's the benefit of a teacher showing what he's shown on this pink carbon, but it's okay. Shows us his red bond, makes sure that we're following everything correctly. O minus. Notice how this is a basic reaction, so we're not seeing cations. We're seeing anions in this reaction. Nice. Keep drawing it. Love it. Think a second. This does look like it's going to create... I'm debating diastereomers or enantiomers. I think it's going to be diastereomers. Because that's a stereocenter. That's a stereocenter. Yeah, so it creates diastereomers. The thing here is a chiral center at the top part of the red bond. The thing at the bottom is a chiral center. Again, there is no chiral catalysis going on here, so it could be RR, SS, RS, SR. He just said what I said about how you're not going to see the 1, 2, 3. Ooh, it'd be so ugly, right? 1, 2, 3. Which would be a 1, 2, 3. Yeah, you very rarely can make a 3-membered ring. Those orbitals are hard to align. It's possible. I did some research on spring-loaded reagents where the Barron group had some cool ways to make reagents that were very, very ready to react because they were so strained. But they were fun to make too, but... Yeah, let me even just show you really quick. Barron group spring-loaded reactants, you might call it? I don't know what you would call it. Spring-loaded reagents. Really, really cool stuff. Oh, great point. He's reminding us, too, that no matter what, this is going to undergo dehydration. So what I just talked about, kind of irrelevant. You're going to form... the chiral centers I was talking about earlier are gone. You go all the way to the alkene. He's reminding us about a tricky couple of quiz or test questions where part of our learning objectives are being able to predict the aldehyde and or ketone, right? The aldehyde or ketone and or the aldehyde or ketones that produced the products you see. It's called retrosynthesis, being able to look at something and saying, I wonder where that could come from. And that's what a lot of chemists do in their day-to-day job. We typically know what we want to make, and so the chemist has to, in their head, instead of thinking about reactions in a forward sense, they have to look at compounds and break them apart going backwards. And so we often teach a lot of forward synthesis. You know, this reaction makes this thing, but we want to leave that learning objective in there of starting to convince students they need to be able to look backwards. What reagents made this compound that he has in the bottom left with the alpha beta, the 5-membered ring with the alkene? Being able to think backwards is very important for the practicing chemist because that's typically what we do in real life. starting to talk about, let me pause. He's starting to talk about how, again, so look at this compound to our right and start to think about in our head, what has to be the starting material? If I want to make this molecule, how would I break it? Where would the carbonyl be? And how do I design starting material that doesn't screw me up? For the most part, should react somewhat cleanly. And I see an aldehyde here that I think he might want to use, but I'm beginning to question at least, I wonder how he's going to make it so we don't have a lot of issues with. Oh, I wonder, can we pre-make the enolate? Maybe he's going to talk about you pre-make the enolate and then add your electrophile in dropwise. You take advantage of concentration. I'm not sure what he's going to talk about, but I know that's one method. Before we come back to this, I'm going to use the bathroom real quick. He's asking us to predict some of the molecules for this. Where's my chem draw? Fire then, yep, I know. Let's just start with the simple answer. Great. Think about, can we do this intermolecular? Yeah, we could do it intermolecular, right? No, we can't. Boom, 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 boom. Sterically, this one's better to get. Don't know why we wouldn't go after this one. Are there other possibilities? Are there other ways to do this molecule? Ooh, it is intermolecular. Wait, no. That can't be right. Ah, okay, good. Great, so what I said. Phew! Woo! I was really worried. I didn't see intermolecular. I didn't think it was possible. It's not. Yeah, love it. Yeah, not the best setup. We're running into the problem at the start of lecture. And the more substituted alkenes, more stable thermodynamically. Kinetically, the green ones are easier to access. Easier for the nucleophile to pick them off. you do it really cold, I think he's going to talk about what I said earlier about dropping in your electrophile, about how you design the reaction, not even your starting reactants, but how you run the reaction. I think is going to be where he's going to go with this. I think we do it super cold with LDA. LDA is a bulky base. Please talk about LDA and make it cold. Please LDA and cold, and we drop in our electrophile. I think that's going to be the point. Yes! Oh, he's giving us lore. So again, just reminding students that if we think about the two possible enolates that can form, this is the more substituted alkene, so thermodynamically more stable, which to us as a reminder, if I pull up a paint, right, if I think about a reaction coordinate diagram and I have T is, or not R, T, let's say R, my red line is equal to my thermodynamic, and my blue line, which is typically what I run in cold, my blue line is equal to my kinetic product. What's nice about kinetic things is you go through something that's easier to do, but you don't go to as stable as a product. The red thing is you start at the same place, so we'll kind of dot, dot, but you go through a higher energy barrier, but you get to a more stable thing. And so the goal is that if you run it cold, go blue line. If you run it cold, you go the blue line. And so he's going to, I think, run this reaction cold to go through the blue line. We won't go to as stable of an alkene. Let's add that note. All right, there's this hyperconjugation thing going on that's pretty neat with the red pathway, but we don't want to react that. So gotta talk to Allie. And talking about how we saw this in previous classes, dienes, HCl, Diels-Alder. Great, shows what I showed, and this my poor drawing. reminding you delta G is what the y-axis is. It's how, well, technically it's the free energy, but in some ways I like to relate it to K values. But that's not super helpful necessarily here. The higher your activation barrier, the slower you'll approach equilibrium, because we got to remember that how fast something happens and what side of the equilibrium it favors are different discussions. If you just look at where you start and where you end, you're thinking about overall in terms of equilibrium, where you start and where you end. Overall equilibrium can tell you, well, the lower your energy on the final thing, the more of the equilibrium is going to favor that side of the reaction. But the kinetics of the reaction, how fast do you approach equilibrium, not discussing which side is more favored, but discussing how do you get from one side to the other. Now you move into kinetics. The bigger your activation barrier, the longer it takes for you to get to your equilibrium. Like rust takes a long time. Burning wood is very fast. Burning wood, real quick, small activation energy, get your flame, get your spark, and then it just keeps feeding itself because it's making energy and getting you over the hump. But rust takes a longer time, even though you will eventually rust the metal completely. It takes a little bit longer because you don't have as much energy feeding into the system. I can't wait to teach Chem 150 again. I'm going to just take a little relaxed state as I keep thinking, but... Get rid of NaOH, get LDA in here. We need LDA. Okay. Not LDA, but... He's gonna bring in LDA. Yes! So let's make a note. Cool. Very cool. And he's going to talk about what most of the learning objectives in this class, what we're going back for. Let's adjust this in real time really quick. So what this lecture has done has allowed me to go into my canvas for a second and say, okay, if I go back a little bit, if I go to the previous class, I'm going to edit this and say, okay, Okay, I'm going to say blue things are midterm 2 learning objectives. Now that we've passed midterm 1, no one's as worried about that anymore. So get rid of identical here. Get rid of this now. And we should remind students that these things have now come up. Crossed all, ring strain, yep, that's been talked about. Draw the structure of LDA, yes, yes. So let's save that. Let's go back here. I probably lost that video, didn't I? Okay. He's showing us something that's going to happen here. That's a little because we have an ester. We're not going to make the alkene. We're not going to do dehydration anymore. Something else is going to happen. I think that's what the next lecture is about. So, okay, order of addition and shows Claisen coming. So class 7 is coming up next. Great. So let's adjust our discussion board a second to tell students that we are now moving on to so again, if students want to watch now, me watching class 7 starts at 1 hour and 15. One 116 about. Great. Make the enolate first. Doing more of a SN2. KH. Hydride base, I see. H minus. Small base. If I make a small base, I'd like to coordinate that one. My thought is it's probably going to be C. Because certainly the first thing you create, so after step, so what's happening here as he's talking, I'll just go through it. So step 1 gives us the enolate here, then we're going to either side it's symmetrical. Then we're going to form this compound after adding step 2. Then if we add a H minus, a little tiny base, and we don't seem to have much temperature control. And so I would say that both this H here could be attacked. Both this H could be attacked. It's pretty small, so I'm pretty confident saying that it can attack here. It could also attack here. And so it is possible that we might add the ethyl group here. Like, that's one product if we attack the kinetic one. But also, if we go the other... Well, let me be a little better at this. So we go here. Step 1 brings us to this compound. Ignore this, it should be negative, but I don't want to spend too much time worrying about that. goes here, goes here, goes here, attacks the CH3 thing. So then we got this compound. Then I think we kind of diverge. Either we go here or we go here. Either we do boom, boom, or we go boom, 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 boom. And then we would go to either this product or we would go to that one. So, let me make sure I return this and this. So I guess the question that he's proposing is it C or is it B? Which one makes sense? If we have a small h minus, small h minus makes me feel like we're probably going to make this one, is my guess, is what we're going to have to say. It should be able to easily abstract that proton. Create a more stable... Well, wait a second. Think. Yeah. And just because I have the time, let's throw this in. And he says use the bulky base if you want to go. If you want to go here, you use a bulky base. So let's write that in, just as a reminder. Big old base coming in. Okay, so now let's look at a new one. So, great, I have this. I'm going to get rid of this for now. That's in the video. So, he's looking at this one, O-phenyl. Oh, I think we're going to do a Claisen. And so he's going to kind of mess with us a little bit. So, let's do it ahead of time. So, let's think about this together. So, boom, 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 boom. And if I write P, does it show up as phenyl? How about a capital P? Great. So we have this compound here in the presence of a arguably not great base, but I guess technically maybe okay. I think we're going to go to the enolate first. So we'll make this. Then this is going to react with another version of itself. So we'll have this here. Then we'll say this goes over here, goes here, 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 here. And then we got to write some funny things. So we've got O phenyl that we just attacked, and then we have O, and we have great. And so now I have a Chem 202 tetrahedral intermediate. In this case, once I attack this one, I think I'm going to kick off the... I'm going to probably kick off the leaving group in this case. Make sure that the... right, if I protonated it to an H, I might be able to go through some condensation type thing, but I probably won't. Before anything happens, I bet this... Let's kind of move this all over. All right, once I get to this intermediate here, I think I'm going to kick down and kick off that group. So we're going to go kick down, kick off this group, and now, Control-Shift-K, I've got this compound here, which, interestingly enough, will be, I wonder some things about what we're going to talk about how we just made a very acidic proton. I'm going to want to enolate the heck out of this proton because now it's going to be stable by 2 carbonyl groups. So that might be a little bit of an issue and might enolate further. But based on what I'm seeing here, I would predict that D is what I am showing here for the most part. Let me see. Boom, 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 boom. Go in, go out, go down. And so my answer looks most like C. So I'm seeing C as my answer. Let's look at the other ones. A. Could A happen? Where could A happen? I'm just not seeing A at all as being a possibility. Wait a second. Well, think a second. No, I don't see that. B's not happening because we need to kick out the good leaving group. We'd never kick out a CH3 minus. What about D? What is he doing in D? In D, he's protonating the tetrahedral intermediate, which could dehydrate. So it has to be C. Definitely going to be C. But I want to talk about this proton. I hope he talks about this proton. I think the argument is probably going to be that once you do deprotonate this, although it is the most acidic proton now, its negative charge is less nucleophilic than it is over here because it's spread out. So he's saying the Claisen is what's happening. Can't put in OH minus because you do tetrahedral intermediates. He's just talking about, you know, let this side reaction happen. He's saying let this happen, but it doesn't do anything. Inhalate. Attacks another. Go back to 202. Now he's talking about this H. This is the learning objective 2, why we need 2 alpha protons. Because we want to trap it in this new acidic, more acidic proton. We need a proton there. That's why we need the 2 alpha hydrogens. Just to show you the other way. So let's kind of take this compound as he's talking. All right, what's the problem? Creates this product here, which now is going to enolize here. That's the problem, child, that now exists. Because we don't have the more stable pKa. It's missing here. We're missing, if I show a carbon there, Oh, he even says it goes backwards. Do I believe that? Yeah, I guess I can say that because it's a pretty stable kicked out group. Also goes back. Anion, not so bad. Poor Keith. He talks for a second about homolumo, orbitals, nodes, and all that kind of stuff. What he's saying is that this pi system, which is what he's focusing on when he's talking about these psi things, this pi system, let's kind of draw it over here, in a super, well, let's keep it somewhat involved with what he's saying. It's not going to be perfectly well drawn, so just give me a little bit of a break. He's kind of saying that, of course, there's the two pure, oops, those are not p orbitals. Let's also put in some O's. Let's make them double bonded. Okay, excuse the bad orbitals here, but he's basically saying that. So in this pi system, there's 2 electrons here, there's 2 electrons here, and then because this is an anion, let's just put a little anion sign, there's 2 electrons there. So this is a 6 electron pi system. And so in our first one, we can have 2 electrons where there is no node. So we put 2 electrons in the no nodes. And then we're going to put 2 electrons. Let's go up in energy. Two electrons can then go into the 1 node, and then the last 2 electrons in our 6 pi system go into 2 nodes. And so let's look at those a second. Again, forgive the poorly drawn p orbitals, but now if I want to put in a singular node on this system, I'm going to flip this one. And the node is, let's do a line. All right, there's the node. Let's make the bond dashed. So there's our first kind of node. And then we'll have to expand this out just a touch. And then in the last one, we're going to need to have 2 nodes, which flip this one back. And so I'm going to flip this one now. Flip this one now. And so again, not super well shown. Can I adjust it just a bit? Yeah, I can. Great. There's one node there. And there's the other node there. So that's what he's doing this all in his head, and his students are all doing this in their head, or they're claiming to some degree that they're doing this in their head, where these 6 electrons, first, the most stable, all of the p orbitals align, there is no nodes, these electrons are flowing perfectly and stabilized. 2 more electrons are now filling these pi orbitals where one of them is actually flipped, and so now they have to use their wave-like abilities to cross this node. And then finally, the most active ones, the ones that are, I guess you would say the HOMO in this reaction, the psi, he's calling it psi 3, or kind of level 3 of this pi system would have 2 nodes, which we would be able to produce them here and here. And then we need to flip this orbital, so over here's one space, here's another space, there's a second space. Showing us an intramolecular Claisen. One question that I have that, well, actually I won't push in my question yet, but I do have a question about, like I said, expert level question of something that I'm curious about. No, that wouldn't work. I'm just goofing on things on myself. I think I answered my own question. I was trying to think of other ways to put 2 nodes in a molecule, and I don't think it's possible. Or it is. It is, actually. Why wouldn't you do that one? Why would I rather have a node there? Stability, probably. Why not? I'll show you what I'm thinking about. So one thing I'm thinking about too is, what about this 2-noder? Oh, that's why. I can't do that. No, I can't. It still works. So this is another way to envision possibly 2 nodes, right? Both of these have 2 nodes. Why isn't it this one? What are my thoughts? Your nodal space where you're saying electrons cannot be is in between 2 atoms, which would break this apart. And so if I'm filling this with electrons, I'm breaking the C-double-O bond, which isn't ideal. Whereas here, I'm putting the node on an atom. And so there's less electron density on the atom itself, but that's okay because I do want to form bonds. I'm not so worried about electron density on my atom. So I think that's why this is, although possible to create another 2-node system, and there's probably other ones we can generate, but I think this one is the most stable energetically. Okay, what did he have them do that I missed? As I was lost in my own world. He's probably showing some sort of... Yep, he's showing a pull everywhere question. So let's skip ahead until we see what this pull everywhere question is. Great. Okay, so let's do this one now. So let's delete all this stuff. Okay, so in here, how do I kind of deal with this problem? So, oops, I made the wrong molecule, so let's see how fast I can fix it. Okay, so that looks right to me. Just double check. Great. Okay. So we have a compound here. First thing I want to point out to myself and what students should probably do is let's put in all of our possible alpha our alpha H's that might react. So here's all the possible ones. And if I do this one, I go 1, 2, 3, 4, 5-membered ring. Okay, great. Here, if I go 1, 2, 3, 4-membered ring, 1, 2, 3-membered ring. That's probably not going to be it. How about here? That'll be 1, 2, 3, 4-membered ring, 1, 2, 3, 4, 5-membered ring, but not symmetrical. Well, is symmetrical? No, is not symmetrical. Or 1, 2, 3. Wait. 1, 2, 3, 4, 5-membered ring. 1, 2, 3, 4-membered ring. Okay, so what I'm doing right now is like, so for this red carbon, I'm saying this is the start of the ring. Let's count to the carbonyl. So 1, 2, or sorry, count this as 1, 2, 3-membered ring. No, 1, 2, 3, 4, 5-membered ring. Yeah, reasonable. Next one. Again, counting my way over. So let's say 1, 2, 3-membered ring. Nope. 1, 2, 3, 4-membered ring. Nope. 5's still more likely. So that one's definitely not going to be the one. So I'm going to even get rid of that one because that one's definitely not going to do anything. Let's look at this one. Let's make this one my new blue one to interrogate. 1, 2, 3, 4. Nope. 1, 2, 3, 4, 5. Yep. So I'm going to leave it. It's a 5-membered one. I think it's still valuable to think about. So next one is this one here, the green one. And the less let's make sure we're right before we say it. Yeah, this one is not as thermodynamically stable, but still we can at least consider it really quickly. So 1, 2, 3, 4, 5, 6, 7. Ugh, 1, 2, 3, 4, 5, 6, 7, 8. So make some larger rings possible, but I let's see what we're using. Yeah, it's O-ethyl is a kind of a bulkier base, so it's something to consider. I think that you could be making those larger rings. The larger your rings get, the less likely those orbitals are to do intermolecular. I'm not 100% sure. I haven't seen statistics on that. I'd like to see some. I'd love to see the actual research paper that looked at these molecules to think a little bit more about them critically. But for now, I'm going to let that one go. So I'm left between these two are both possible. Which one makes a better... Ooh, that's a better pi system. I love that pi system. So what I saw is that if I form an alkene off of the blue one, so if I make the blue pathway, right, that would be here, here. I make that enolate, whereas over here I can also make that one and that one. Get rid of that for a second. That one's kind of nice. Actually, it's not conjugated. So which one do I form? This one is more substituted. This one's less substituted, so likely it's going to be this one is the thermodynamic sink. So possible that that one's happening, but for now I'm going to let that one go. And then we're going to go 1, 2, 3, 4, 5. 1, 2. So we're likely going to, let's get rid of this and say it's likely to attack this carbonyl. And I don't think ChemDraw is going to do a great job at this, but let's at least give it a shot. So if I make that bond and I make you a 1, you kick this off. Can you reorient yourself? You can. So that looks like it's probably going to be the product that we're going to form. And I went a little fast there, but. Great reminder. That's a good reminder. So this, what's the problem with this product is, well, there's not necessarily a problem. The one thing we want to consider is that the green one, or the, well, I can still form that bond there. Well, let me think a little bit more carefully about these things. So I can do this one, great, or I can do that one, which is also possible. Then it attacks the blue, makes that one, or I do this one. Is that compound? Are those the same? Be careful. All right, let's go back and be a little bit more thoughtful about this. Okay, so I have this. I go here, here, attack here, up, down, kick off this group. Okay, readjust yourself so you look like this. Check a second. I have that. That looks great. Now we're going to flip it. Ah, so that is the wrong pathway. Cool. So if you go this way, red attacks blue. Okay, I want to be a little bit better about how I present this if a student is reviewing this video, so let's go back to how I thought about this. So one mistake I made is when you have lots of enolates, make sure you do an enolate that has 2 alpha carbons. And so in the one he had, we don't do the red one because, so let's look at his options. red and green CHs are only one alpha CH. So although it's happening, the reverse reaction is also happening, pulling that out of the equilibrium. So we have to form this enolate here. And then now we ask what member ring. And so instead of highlighting these red and green, I'm going to get rid of those. I'm going to start considering this one and this one. And so here we'll make our color green, and here we'll make our color red. And so we go 1, 2, 3, 4. Green carbon is 4. Red carbon is 1, 2, 3, 4, 5 is 5 ring. And so that's why I can then take this compound, and thanks to ChemDraw's magic, I can say, all right, kick down, kick off, attack, and kick off this group here as the Claisen does. Clean it up, which is Control-Shift-K on Windows, and now I'm here. And let's change this all to black and remind ourselves that this is the important part. Purple H is the key to keeping this reaction clean. What I mean by clean is that we're making less products. Gonna make a carboxylic acid, right? To an acid. Yes, I agree. Go back to Chem 202. Your ester leaves. You're making the carboxylic acid, you're making the ester part of the molecule ahead. Electrophilic with the acid. Water adds, kicks out the ester. Student, 1 second. Hello, hello, hello. Are you available to go into a Zoom call right now? I have some questions regarding the exam and contract grading. For now, I'm gonna say no. I just want to make sure I'm ready for class tomorrow. But in general, it's likely that your questions probably will belong on Canvas discussion, or we can talk about it in class. Either stay at the end of class, or if I have some time for questions in class, bring up your questions there. But for now, my guess is that probably most of your questions will belong in class Canvas, which once I kind of feel like I'm ready for class tomorrow, I'm going to jump into my email inbox, I'm going to jump into my Canvas discussion boards and start kind of getting back into my networking, I guess is what I'm jokingly calling it. But let me ask you this. Is there anything immediate that you really want answered? Either ask it publicly, or we can jump into a Zoom room real quick if we have like a real personal or really time-sensitive thing. I don't think there is a big issue. Hopefully you read my announcement that says exam grades are coming soon. We have somebody who's taking an exam still who is traveling, so I haven't released the key yet. That'll be coming tomorrow. Grades should come Thursday or Friday. Contract grading, something that a student brought up is like, again, a reminder that you're going to readjust your contract at the end of class if you don't get an A in the class based on the contract you chose, and that's why you want to be thinking ahead of time. How can I do more in this class so I can negotiate better? But no one's locked into a contract. These contracts aren't, you have to follow this. The end of the class, the negotiation period says, did you go above and beyond in your contract in some areas, and your exam scores weren't so great, you underachieved in some parts of your contract, and so how can you show me that you did some work ahead of time to go above your contract in some areas. So, but yeah, let me know if there's any basic questions. I'll answer those, but I'm going to keep watching this and kind of watch chat for a second. But put it in discussion is my first thing. If you want to chat right now, we can, though. I should have made a timestamp, but I didn't really say anything that interesting or new, in my opinion. Oh, this is so cool. So he's starting to walk into how he's basically saying, we just did a bunch of stuff that feels like it's more Chem 202, 203 stuff. How is this going to apply to macromolecules? Like, it feels like I'm not in a macromolecules class. And he's talking about how I think the creation of CO2 by doing decarboxylation, by having the carboxylic acid, you can see CO2 there. I need a response on top. Okay, great. And remember that once I fix Canvas discussions, you can post anonymously. And sorry for spelling anonymously wrong, but I'm too busy on other stuff. So anyways, so that's why it's okay if I completely understand being uncomfortable. That's why there's the anonymous discussion board. So you're not necessarily attaching your name to a lot of the stuff. Yeah, you got to choose the right board to post it in, but that's the point, is that you shouldn't tell everybody everything. Back to what I was saying. So I think he's about to say this class, as we end class 6 and 7 lectures that Dr. W is giving us, he's about to say how when you have a gas in a system, usually a gas leaves the system, or entropy reasons why you're creating two molecules can drive nature to do certain things. And so nature, a lot of the times, I bet, is going to use decarboxylation to, trick is not the right word, but to take advantage of equilibrium to drive forward certain things. But let's see what he says. Cool. Cool. He's asking us which bond he's about to show us. That's the bond that broke. Kind of like an enolate again had to be formed. The H gets deprotonated. O comes in, goes over, goes up, goes back, gets protonated. It has to break into the carbonyl. Or if this sounds, both are carbonyls. It has to break into what's going to be the ketone. He's asking which way does it break. Starts to talk about ester to acid to CO2 to bond breaking CC bonds to get back to macro molecules. Yep, see, it has to, so what I was saying is it has to, when he brings the electrons from the O in to make CO2, granted it looks protonated CO2, so we'll have to make it a little bit cleaner later, but he's focusing on the CC bond that he's breaking. The two electrons that are here in the CC bond break into what's going to be the ketone, because they're stabilized by what would be at first glance effectively, again, an enolate. This enolate is showing up again and again and again and again. This the class is kind of beautiful in some ways. That first day of lecture says to you acid, carbonyl, all that kind of stuff. But when you do a base, you make these enolates, and we do a lot of stuff with these enolates. Cool. Oh, cool. Oh, beautiful. Dr. W. Applause. 6-membered ring. Diels alder almost. Beautiful. Diels alder, but not exactly. So interestingly enough, the learning objective talks about under acidic or basic conditions. Here, it's neither. He's saying that he's proposing that this is just in the presence of enough heat, you can get this thing to happen, regardless of if it's acidic or not acidic. Or, well, I should say it looks a little acidic because he got to the acid under acidic conditions. So possibly he might want some acidic conditions. But I would say, in some ways, maybe I should say the 6-member transition state. Let's make a note on that to myself that I am not 100% sure and I want to go back on. Consider learning objective 5. Do we want acid base or just the 6-member aromatic transition state talked at end of class? So we might fix that up a little bit. But okay, great. Moving on. Edit this up. Class 8 starts at 2:09 about. Okay, moving on. So they took the midterm. Okay. We got some new learning objectives. We'll have to see if they get covered. I want to leave in here the fact that I'm not 100% confident on. Oh, did I miscount? Maybe I miscounted. Oh, no. No, I don't think I did. So we've done 6, 7. Now we're on 8, but I want to consider that I might need to fix up 7's one here. Let's go back to the schedule a second. Okay, class is going to be on... Well, we have to watch 2 more videos, basically, class 8 and 9. Because class 10 will be on the midterm. And, you know, maybe I'll just watch that video anyways to talk about it in class a little bit, because that's not a bad idea. So, all right, let's get going to 8. Alright, moving on to class 8. His 7. I must have miscounted something. I don't know. Doesn't matter. We'll keep watching, though. Ugh. He's kind of saying we just finished Claisen. Those will be important. The decarboxylation is probably super important. But now he's saying we need to kind of take a step back and think about some other things. And I think we're going to start getting into even looking at the learning objectives. Why is water so important to life? Maybe because it can both protonate and deprotonate. I guess we'll see. Or the pH of it is probably important. Hydrophobic effect. Interesting. We talked about this in a previous chem class. And I mostly talked about microstates, if I remember correctly. Entropy. We'll see how it applies here. Draw both the D and L amino acids in the Fischer projection. Fairly easy for us to do, I think, based on our previous work with Fischer projections. Okay, great. Prevalent form. So this is something that a student brought to me in a previous office hour where I was like, oh, dang, man, I got to look this stuff up a little bit. Because I remember recording it and listening to it a little bit, but I didn't really think about it that much. And this is where I think we'll start to see some double cations. But regardless, the cool thing is we're coming to amino acids. We're not talking sugars no more. We're going to have some amines, some nitrogens. So let's see what more of this lecture covers. Biology. Ugh. Just kidding. Biology's okay. So what are proteins? Getting back to macromolecules. Last couple classes were a little bit not so macromolecule. I should probably listen to that announcement in case it's important. What is he saying? Is there a way to speed up the speed of this video? So he's asking the class, what is the function of proteins? What is the purpose of proteins? I'm trying to think, what do I even know about proteins? I believe it's like the energy. Like, this is how you make energy. You make, I think it's ATP or something. They're a catalytic thing. They do chemistry. And when I say they do chemistry, they make and break bonds we need to live, which involves probably energy. ATP, I bet, will come up soon. I think it's ATP. I've never taken biochem. I remember some things from biology in high school about this stuff. But this is partially why I'm so excited to be in this class and to be teaching it, and, well, kind of teaching it, letting Dr. W do most of the teaching, and I give you the expert opinion on things. Let me be more clear. The expert opinion of the expert student. Like, I probably would be the most question-asking student in this lecture if I could disguise myself to be a college student again and be like, oh, Dr. W, what about these things? You know, I feel pretty comfortable with a lot of the chemistry. The last two classes, loved it. All the chemistry I know. But, you know, proteins, I know about them. I've read about them briefly in my PhD. I took a biology class in high school, but I never took biochemistry. I never understood biochemistry. So I always stayed away from teaching 204. I was like, nah, not my cup of tea. But as I'm taking it, I like this course a lot. It's almost that missing link sometimes where I love talking about small molecules, drugs. I love talking about, you know, the quantum world, the waves and particles. That's all fun. But what's always been missing from my lectures, from my teaching, is applying it to, like, the human body, the real life, what people have every day around them. And so this is that missing link that's been helpful for me to get more interested in. So, and is like, it's a catalysis kind of thing that does chemistry in the body. Is this hemoglobin, maybe? Looks like O2 to me. He's bringing us back to this. That looks like O2 to me. And it also looks like, I think, hemoglobin. Is this what is in our lungs? Affect equilibrium? It is hemoglobin. Okay, good. He's telling us to focus on this. That's what made me think hemoglobin. Oxygen. These big barrels, I think they're called? Helixes. And I know what he's going to go with this. So this was another topic that came up, I think in Chem 150 or 202. It's like, well, why do they form these helixes? Technically intra, but you will know the term intermolecular forces, IMFs. That's what causes different things to stick together. But if you have in one compound things that are sticking together, that's what causes the barrel, is its intramolecular forces. Still an IMF, but be careful what the I means. It's different. Intermolecular, intramolecular. H bonding is what loops them together. Folding, yep. So a protein acts as a transporter. It's like, my guess is, where is he going with this? He said that the first thing proteins can do is make and break bonds. The second thing is, if we think about equilibrium, not in a chemistry sense, but in the equilibrium of moving oxygen out of the air and into your lungs and into your blood, into your heart, and all the places oxygen needs to go, the equilibrium of getting it to move out of the air into your lungs across the body, that equilibrium might need some driving force that proteins are helping with. Not equilibrium of reactions, equilibrium of phases, the transfer of a phase, gas to liquid, transporting. So I'll just say, can transport things across boundaries in the body? I think is what he's saying. So forming bonds, breaking bonds, catalysis, reducing a ketone. ACE is the key to what this protein does, is in this category. He's saying how the body has different ways to reduce than a chemist might in a lab. And so, like, we use really, really strong hydrides, but we can't put that in the body. We'll destroy the rest of our body if we have that. So we need to have a more, quote-unquote, softer way to do reductions in the body than we would do in the lab. In the lab, we use H-. Nature eats a different way than a metal hydride, is what he's saying. I agree. Oh. Right, because O2 is a gas. So how you don't want to have bubbles in your. There's a. Right, to just briefly talk about when you're deep sea diving, right? Part of the problem with deep sea diving is you have to carefully. Once you go, you have to go down slow and you have to come up slow. Because if you come up too fast, gas starts coming out of your blood, and you have these gas molecules in your blood that causes you to go practically crazy underwater. Or even lose consciousness, or worse, or just in extreme pain. And so O2 is a gas, and he's kind of saying that the protein is helping by taking the O2 and letting it stay in its liquid form, or it's attached to the hemoglobin, which keeps it in the blood. You don't have O2 popping out of your blood and causing you to go insane, or have extreme pain. Cross things in the boundary and keep gas in, let's say, a liquid environment. You can, yeah, it's so funny. Anyways. Talking about hair. connective tissues. So let's say what makes us us. Collagen. Heck, I bet like another one would be spider silk. I wonder if that's a protein. But this is the focus. But for this biochemistry course, for macromolecules, we're in this world. This is what I was talking about, but the barrels, right? The barrels are held together by these reaction or by these forces. Interesting. I just want to make it clear again. You got to be careful with your terminology here, because intermolecular forces means the molecules are not covalently bonded. Intramolecular forces mean they're bonded and they fold in on themselves. He's trying to set his students up to have a reference point for why he calls these weak. He's saying, think about the kilojoules per mole of a covalent bond, carbon-carbon, hydrogen-hydrogen. Yeah, just look it up. I'm not sure if I want to memorize these things. I understand how they're helpful for... I mean, I'm sure the more you do chemistry, you will always remember what a bond is after a certain amount of time of teaching it. But for my classes, personally, I don't mind if you have to look it up on your cell phone. But set this reference point for why these forces are weak versus strong. But remind yourself, too, that a collection of weak forces can be quite strong. A collection of many, many small... You know, what is it? 100 small geese. Would you... Oh, I can't remember the joke. Doesn't matter. It's additive. It's very additive. Weak forces that are additively added together can become strong. Talking about how some of these structures have pluses and minuses which interact. That's ionic interactions. Cause a protein to fold. That's where water's going to come into play, the hydrophobic interactions. Why is water so important to life? The hydrophobic effect. Huh. Why do we care about weak bonds? Or we shouldn't call them bonds. Weak interactions. think he's going to this point. A lot of weak things can become strong. Yep, he just made the point. Additive. Brings up a nice point that I wasn't thinking about. The weak forces allow for a little bit of change in it. Yeah, it's hydrophobic effect. Hydrophobic effect. Hydrophobic effect. Careful! Did I just lose all those spiritual people? No, God couldn't have done it this way. And granted, we're saying is thought to arise, so we're leaving this space open. And this is something, let me just pause for a second and reflect. I'm very curious, and I would love eventually to find some aliens out there where, you know, water and carbon is our universe, our structure of life, why we possibly evolved to look the way we do, why our body and chemistry evolved the way it did. But there might be life out there that evolved with other solvents of their life. Maybe there's silicon-based life forms out there, right? There's a whole periodic table behind me of other life forms that might not be as carbon-based as we, or as water-reliant as we are. And maybe one, I probably won't meet them, but maybe my grandchild's grandchild, which I won't have, my adopted grandchild's grandchild might meet. But yeah, okay. So but I agree. On Earth, water is the key to a lot of our life. Not DMSO, not sulfur-based. The reason we have fatty parts of our body is because they don't dissolve in water. They are very not dipole filled. If they're not dipole filled, right? If you have, so what he's trying to say is, you know, the reason we have these quote-unquote fatty things going on, and what we mean in chemistry, when we say something's fatty, what we're really saying is that it's mostly carbon-based, and so there isn't dipoles in here that, right, if we think about water, if I overdo it, and just be aware I'm overdoing it because I haven't yet figured out how to do partial positives and partial negatives, but if I overdo it and I say, this is a charged molecule, and so when it comes to something that's more neutral, the intermolecular forces here push water away. So water can't necessarily cross this barrier. But there's probably parts of our body that have, right? If you think about soap, for example, the reason soap works is because there's a part of soap, right? This is not the fatty part of soap. This is the part of soap that gets it into water and then pulls. All your oil got attached to this. So all the oily junk, clip, picked all this stuff, all my oily junk, fatty things go here. So that's where all this stuff happens, and then the universal solvent in this stuff, right? That's how I get it to go into water, is it pulls it there. Anyways. Oh, truly the miracle of life, right? How do we take things that are unfeeling, right? All these structures heal. Unfeeling, nothing, no emotions, no thoughts of a greater future. And how do we get life out of them? Man, this is why biology scares me. Nice. We're water. Welcome. Welcome, water. Keep drinking. Keep hydrated. But he's trying to, I think, lead us to the point of, why is this the case? We know we can measure that we're mostly water, but why did life evolve to have a lot of water involved in it? And I think the hydrophobic effect is huge. I think the solvating effect of water being a polar molecule is super important for separating structures that if you have something really polar in your body, then water is going to dissolve it. If you have something in your body that's not very polar, because water is in most of our bodies, it won't dissolve it. And so water needs to be on one end of the spectrum, or the universal solvent of life, whatever galactic life you have. There's probably an argument to be made that whatever your universal solvent is needs to be on one end of the spectrum. It either needs to be your universal solvent is very oily, hexane, or your universal solvent is more like water, very polar, because then you allow for there to be membranes that are not passable by your universal solvent, your life solvent. I shouldn't say universal solvent. That's a whole other research area. And if you have a universal solvent, you also need a universal container. Anyways, but I think the solvent of life needs to be on one end of the spectrum, either really oily or, in our case, really polar, so you can have separation in your body from where you want your solvent to go and not go. But anyways, because that's what the hydrophobic effect is going to go into. That's bonkers that lungs is 90% water. That's crazy. Again, show me how you calculate this, but I'll buy it for now. He's asking what's so special about water. It's polar. He agrees. Polarity's huge. What else? It donates H. It can be both acidic and basic. Hydrogen bonding, I guess, would be another thing. It's an OH. Goes back to its polarity. So, okay. Yep. He's asking why is the bond angle 104.5 degrees. The two lone pairs are pushing against each other more, whereas the other two are shared between the O and the H. So they're less diffuse, would be one way I guess try to describe it, but that might not be the best word. Or you could even say to some degree the hybridization is more... Well, I think he's saying that it's not necessarily SP3 because he's going to make them like SP2 point something, give it more S character to stabilize them. SP3 is 109.5. Because SP3 109.5, SP2 120. So, oh, it's more. It would be more then. So it's like SP 3.1. Or whatever he's going to write. And so now he's throwing out the fun part of hybridization. You heard S and P, you heard SP, SP2, SP3. But when we get into, you know, the reality of orbitals and how complicated they really can get, you get some of these decimal-based SP systems. Asking which one has more S character. So again, think about what you know about SP3 bond angles versus SP2 bond angles. Would you rather put S, you want to put it in an S orbital? Mm-hmm. Let me just pause for a second and be a student in the classroom for a second. One thing I have to be careful of here when I'm thinking about this kind of stuff, from, you know, putting myself in the perspective of what do we know up to this point? What would if I say I'm the average Emory student in some ways, you are limited by orbitals to only go up to SP3. There is no SP3.1 because I only have 3 3p orbitals to mix. So I can only go down in character. I can only go down to SP3, SP2.9, SP whatever. So it is actually quite an interesting question to say, how do we get these bond angles of 104.5 if we don't have extra p orbitals to donate? Because H only has s orbitals, O only has p orbitals, unless I'm bringing in 2p orbitals or 3p orbitals or d orbitals, which is, I think, you know, as you get more into orbitals, you're like, well, I guess that's technically possible, but this is so bonkers if he's going to go into this. So let's just write this. And so his SP3 plus X is for these interesting. It's a super weird thing to think about, because a student who really understands orbitals should be like going crazy in the class. The fact that he just wrote SP3 plus X. Where are the other P's? There's only 3 P's. PX, PY, PZ. What's going on, Dr. W? And this is why orbitals are not as clear-cut as we made them assume. Right? What? This should make you go bonkers. What? And I think the short answer for the short answer is partially that we are not just dealing with one s orbital. There are 2 s orbitals involved, the one on the oxygen and the one on the hydrogen. So it is possible to have less of a p character, but it does seem awkward how we're describing it here. what I think he's pointing out here, melting point and boiling point, why are they the way they are in this graph? There's not a trend with molecular weight. And heat of vaporization is super odd too. Definitely electronegativity is an issue here that he's bringing up a lot. Let's bring in a table of that just for a second. Right, if I bring that up here. Remind yourself too that when you go to sulfur, look at how you drop in electronegativity, 2.5 versus 3.5. Hydrogen bonding. So before we continue, I just want to remind ourselves what is going on here is the percent of p orbitals that are part of shape. So the red is more p less s. Still use 3p, but less s. And so that's how you're getting that fraction. Again, that would be like what I'd expect students, or not, well, no student would do that in class, but that could be a fun thing that like a really like student following the class along would be shocked that that was brought up, that you could have more p more than 3. But you can, you just have to make s less, and so p percentage-wise becomes more. It's not that you have more p's coming out of nowhere. Oops. So again, the structure we're looking at now is water, but in some ways the water is a little funky looking because the artist has put in actual bonds between compounds, and I'm not crazy about some of these bonds. I'm not sure why an O is connected to an O. That doesn't make a whole lot of sense to me, but yeah, it seems a little weird. So I'm a little bit confused by this picture, but he's effectively talking about butane in the middle is a hydrophobic molecule. So again, butane, if we walk away from this discussion of that being like, whoa, that might have felt a little weird. All right, butane is a very non-polar molecule. So I have my butane here, and if I have water around it, what is going to go on with all this stuff? So, because water itself can certainly, you know, cage up to itself in some degree, where these interactions, I think I can draw hydrogen bonding, these interactions here and here are what's kind of caging water around this molecule to some degree. So caging, and let's just kind of keep it looking like that. He's asking, why does it make a cage around it? Saying it increases the entropy of water, which is what we talked about in an earlier class, Chem, whatever, 150, 202. The amount you want to because if you, well, we'll let him show a picture before we talk about it. So we are going back to entropy, which is good. Such an important formula. We often forget that we learned this one in Chem 150, but how important this formula is. We're dealing with delta S here. So this is going to be really cool because this is like, it's actually probably more important that when you're considering these things, what you want to do is say, okay, I have this and excuse how some of these interactions aren't great, but right, I can have, oops, no, please come back. No, did I lose it? No, come back, ChemDraw, don't freeze. ChemDraw. I think I just froze my ChemDraw. Old program problems, that's okay. Alright, we'll keep watching. But I want to get ChemDraw back. So what's important about this discussion is that on the previous slide, we only have one oily thing, right? He only has one butane. But what he's moving forward is that to really understand this effect, you kind of need two of them. Because right now I have, so let's count, right? In this first structure here, if I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 24 order of water need to be around the butane, need to be order. And let's just have, also add, let's just say 2 water molecules chilling. And I should do more than 2 water molecules because this is what he's talking about with the bulk idea. So let's also just add 2 water molecules chilling out here. And this is something where maybe part of class I'll have to talk about how I approach entropy and how I think about entropy, because it's about microstates, which is either something you completely understand or you don't understand at all. But what a microstate is like, okay, this is how the waters could be, and then I could take a picture later And after I take a new picture of the molecule, so let's say this line here represents me kind of taking a new look at the water molecules. A new microstate is, well, what if one of the molecules rotate like that? That's a new microstate. And then I look at them a little bit later, and that's a new microstate. It moved over there. And then I take a picture a little bit later, and now this one's like that. And now this one's over here now and slightly shifted this way. Right? Microstates are just taking different pictures of the molecules and saying, how have they changed in relation to one another, their distance from one another, their how they're oriented angle-wise. And so the problem with the caged water is there's not a lot of microstates. It has to stay kind of around the butane and bonded a certain way with other water to be like, we don't really know what this butane thing is about. We don't like bonding with this butane thing. We like bonding with ourselves. And so it cages itself around it. And so what'll happen is once we go from here to here, what we can do is let the butane molecule go over here and yeah, because we need to maybe make a little bit more space, we might say that we need to have a little bit more. All right, let's move that back. We might need to make some more space, so we might need to add in one of those and one of those. But we freed all of these now to mess around however they want, and so now we have 2, 4, 8, 9, 10, or yeah, let me count. 2, 4, 6, 8, 10, 12, 14, 16. And so now I have over here 16 ordered ones. And I've effectively released 4, 8, now I have 10 water molecules chilling, doing whatever they want, doing all sorts of like funky, they're microstating all over the place. They're not worried about having to be around butane a certain way. And so their entropy, their ability to move around in different ways, have different orientations has improved. We're actually reviewing something you might have talked about in, I can't remember if it's Chem 150 or Chem 202. I don't remember which one it is, but it's definitely come in a previous class. Released them, right? So allowed the butanes to come together. What I showed over here come together. Again, notice just for a second, let's go back. Notice just for a second how when he's solvating the oily part, the part of the compound that doesn't have a lot of dipoles in it, notice how the water is not orienting its dipole in a specific way. It is doing, its O is looking at it, now its H's are looking at it, now its O's are looking at it, now its H's are looking at it, because really both parts of the water can solvate the fat to some degree. But the order he's talking about is water itself is ordering itself. Water's OH goes to an O. Water's O goes to an H. Water's O goes to an H, which goes to an O, which goes to an H, which goes to an O. So the water is highly ordered around this fat. And so great. Again, effectively just showing what I showed over here. You have to understand entropy is microstates. Microstates are awesome if you have, like, imagine again, the best way I can explain this is, let's say in class, I had 3 people acting as fat molecules. So 3 people are standing in a room. fat molecule person, another fat molecule person, another fat molecule person. I make them go to different parts of the room, and I say, okay, every fat molecule needs to be surrounded completely by water. The rest of you are water, so go form a circle around water people. Let's at least make a circle of 4. So around my classroom, I have 3 fat molecules, and there is 4, 8, 12 students around those fat molecules. So they are all now around the fat molecule. There's 4, 8, 12 students as water. And the rest of the students that are not surrounding the water are like, I know this would be goofy, but they're dancing around the classroom because that's microstates. When you are quote unquote dancing, these are the microstates of water. Sometimes it's like this, sometimes it's like this. But if you have to solvate a molecule, you can't dance anymore, or not as well. You have to stay locked in a certain formation around your fat molecule. You can't microstate around and do different things with your body. But if we brought those 3 fat students, the students who represent fat molecules, fatty acids, the fatty part of molecules, if we put those 3 people together in a group, we would say, well, the group's bigger, so we can't just have 4 people around them. We might need 8 people around them. But look at the 4 students who used to be locked around a molecule can now join you in your dancing, can now join you in your microstates. I can now take lots of pictures of these extra 4 students going around. And so that's a really interesting way to remind yourself. Entropy is about molecules being able to dance. It's about, I mean, it's art. It's beautiful art. Entropy is really about how many different ways can the molecule, or like dance is about orienting your body in creative ways that people are like, wow, ballet, wow, what is it called? Trap dancing? I don't know. The crazy like worms and stuff. Like, that's microstates, is dancing. If you can't dance, if you have to stay around a molecule and you're locked in, you're not dancing, you don't have many microstates. You don't have any beautiful things to look at. You don't have many different ways to change your orientation. So absolutely fascinating, this idea that he's bringing up here. All right, so again, just to apply it here, here's the 3 students separated in the classroom. Look at how many people have to be around them. Look at how we have all these dancers. These are the free dancers dancing around. But when we move them together, we do need more molecules now overall. Or sorry, so over here, we needed a certain amount of molecules to solvate 1 piece of fat. And that was consistent across all of them. Here, we do need more to do 3, but we don't need as many as we had over here. And so we could count these, but there are more dancers. There are more microstates. There's more water free to tumble around rather than be locked in a formation. I wonder if I can do this. I bet I can do this online with annotations. He's talking about the magic now. Right, he's talking about the magic of all of this, the magic of the hydrophobic effect, the magic of getting as many dancers as possible in your atomic sense, is this naturally happens. You naturally, if your molecule, if your solvent of life is water, which is polar, if there are parts of your molecule that are non-polar, they will spontaneously want to be near each other because of entropy. Because spontaneity is delta G. Spontaneity is literally what delta G represents. So anyways, I'm getting so excited I need to use the bathroom. So we'll be back to keep looking at this class. Alright, we're back, so let's keep watching. Delta G. Delta G by entropy, so I should make that a point. That's what a big part of this lecture is about, is entropy. Do they know what entropy is? Do they know how to think about entropy, not in a scientific way, but in a way that you can understand? Yes! Quick story about my PhD. My boss was like, you're on an amino acid project. You should memorize these. And in the back of my head, I'm like, yes, if I worked with these amino acids for the rest of my life, I'm sure I would naturally memorize them. But I have a cell phone, right? Can't you ask me what any amino acid is and I can find it in a second? Anyways, I don't know. This is my whole issue with why do we memorize things when we have a cell phone. But anyways, love these guys. Different R's, right? Over here. They all share the same core structure, but look at how many different ones they have, these side chains. Whether they're polar, whether they are not polar, whether they're positively charged, negatively charged, depending on the pH of your body. Which is like near 7 because of water. Ah, we should add that. Why is water so important for life? pH. Near 7. Oh, and good point here as well. We're making a Zwitter ion, right? This is Zwitter ion. Let's look it up a second. So the Zwitter ion is kind of interesting because we're gonna get to some interesting things. We're gonna have a cation and an anion in the same place. I spent the first part of lecture or this course, and even a lot of previous courses have talked about if you're in an acidic environment, you should only have cations. If you're in an anionic environment, you should only have anions. Now we're going to remind ourselves that chemistry is about understanding some general rules that are true across the rest of chemistry, but these general rules that you only can have anions or only have cations is not true. It is more stable to have this pKa is 5. What is this pKa? Remind yourself that the pKa of a protonated nitrogen, it's higher. And so your equilibrium is shifted towards having the weaker acid. The weaker acid is a protonated nitrogen. And so it still follows the rules of chemistry, but it feels like we're saying, why do we have an anion and a cation? Remember the fundamental rules of this anion is actually quite stabilized through resonance. This nitrogen is okay with having a little bit of positive charge on it because look electronegativity wise. N is less electronegative than O. O is okay having more negative charge on it, and we have resonance. That's the fundamental rule. He's getting into pKa's right now. He's asking, what is the pKa of an amino acid? You might at first want to say 5, right? A carboxylic acid. All right, let's see if it has it here. Well, let's go to the one I like. Do I have it as a bookmark yet? I don't think I do. Right here. So where's our carboxylic acid? Right there, about 5, 4.8. Protonated nitrogen, though, 11. See how it's higher? Right, we have to deal with water. We have to do water because we're now moving into the body. We have to walk away from my love for DMSO. All right, this is all DMSO down here, but we have to stick in this table. Right? Would you rather have an acid of 5 or would you rather have an acid of 10? You always have the larger pKa. You will always go to the larger pKa acid. So he's showing us why we see on this page. Look at how these are. It doesn't do a good job of showing this, but why are these anions and cations? Because of this table. Asking us DRL. Right, remind yourself for D and L, we have to, well, I guess how is he going to, it's going to be chirality. It's 100% chirality. Fisher projection puts the NH2 to the left. Because what was it for sugars? For sugars, I believe it was... Right, remind yourself that... Let me see if I can pull this image over here somewhere. So if we remember from... If we remember in D and L sugars that the D sugar has the OH to the right. The L sugar has the OH to the left. Here, when we do it here, it's not an aldehyde on top. Now we're going to set the foundation for naming by putting the carboxylic acid up. And we're going to say our NHs are what we're going to focus on, not our O's anymore. But still the same notation applies when we do the Fisher projection. Right, let's do the Fisher projection for this for a second. So if I go into mole view, is that right? Yeah, I think it's mole view. So I'll make both of them for a second. Let's get rid of this. So I have, boom, boom, boom. Right, if I don't put chirality into it, which one is this? Well, let's look at the projection. So, so there I put my carboxylic acid on the top. I took my, normally I look at sp3 things like this, right? We have line, line, wedge, dash. But I'm going to change it so that those two things are going back, these two things are going up. I have drawn the other version, right? I've drawn NH2 on the other one. This is D-alanine. However, if I enforce chirality on some of these things, so this one, if it's wedged, now when I come in, now when I look down this bond, see how now it's on the left of my screen? But if I dash this bond, so notice how carboxylic acid up, my R group down, my NH going left on my screen. But if I dash this bond, if I change the chirality of this bond and re-look at the Fisher projection, oh, now it's on a different part of my screen. Now it's on the right. That's how the chirality and the Fisher projection still applies in this case. Right, ask us RS. So what I want to do is use the right-hand rule, right? So of course I can, very quickly put it into ChemDraw and know the answer. But I want to say to myself, okay, I know my thumb is the H. It's going into the screen. Now the question is, where is 1? So if I go out, I go to a carbon, a nitrogen, and a carbon. Oh, it looks like nitrogen is my 1. Then the next question is, okay, what is the group 2? Well, I can go out from this to a C. That C has either 1 O on it, 2 O on it, the other one has an O, so that's my other one. So boom, boom. This looks to be S. Let's confirm with ChemDraw that this should be S. Yep, we know we're going to be right. S. Great. That's my right hand rule. I break my fingers to go to the carboxylate. And so that's how I know it's going to be S. I can use ChemDraw, but I probably want some way to quickly do R and S, and I think right hand rule is the easiest way because it doesn't require a lot of drawing. It doesn't require a lot of moving things around. As long as you're able to be artistic enough to think physically three-dimensionally, you can do RS all the time. So move, 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 move. It agrees it's S. That's the structure. Remind my clock that I kind of see in my head going this way. And then is it D or L? So we have to, again, kind of adjust ourselves, put our carbonyl on top. Great. Now that our carbonyl's on top, we're going to want to think, what is our R group? We're going to put that back. Here's our asymmetric carbon, so we put it back. So I put those two things back. My NH is going to my left, left, L, L. So this is L. All right, I used that same structure he was showing. This is a cool research question. Why is life chiral and purposely chiral in only one direction? Why are we only L amino acids? How did that happen science-wise? Did we just flip, did you know, whatever you call God flip a coin? There's no clarity yet provided in research as to why did we choose one chirality over another, and what are the consequences of the other chirality. The handedness of life is a research area that's not super well understood. Some people think it's polarization of light. Life is chiral. The handshakes. This is how I explain chirality to students. It's like the point of chirality is if I'm about to shake your hand, depending on what hand so you're going to offer a hand to shake my hand, right? When I meet you, you're going to offer a hand to shake my hand. If I cross the body and cross from the hand you come out and I cross to the other one, that's a handshake. That feels right. But if I bring in my other hand, you're like, what the heck is he doing? This is a weird handshake. If I mirror the arm you bring out for a handshake, that feels weird because our hands are the first things we might realize are actually enantiomers of one another. They are mirror images. You know, if I don't have my ring on, they're mirror images of one another. right? He's reminding us that if you come in with this hand and I come in with that same hand on the other side, not necessarily like a mirror image hand, it's the same chirality. The same chirality shakes well. Different chiralities don't shake so well. Yep, secondary. Starred ones we need to eat. We need to have them. He's showing us all the different R chains. These ones are non-polar. Again, remember that sulfur is not... Where's my electronegativity? Alright, remember that sulfur. It is electronegative, but it's as electronegative as carbon, so that's why it's non-polar. You might think that's polar. It's not. Sulfur's not as polar as O. Why is he separating aromatic from non-aromatic? Because when I bet we are going to go fold up proteins, if we can stack aromatic rings, pi stacking is a form of, depending on how connected things are, intra or intermolecular forces. It's another type. Rather than it being necessarily van der Waal, it would be a pi stacking version maybe of van der Waal, but I got to be careful saying that because I'm not sure if that's accurate. Pi stacking is probably better, but... And you remember as well, yeah, these are a little bit more dipole-esque. We are starting to have some electronegativity that is different than carbon, but be aware that they are in a aromatic system. These electrons can have some p orbital or some p likeness to them that makes them a little bit lower in energy because they're in this conjugated system. Honor for this whole being about water lecture, keep drinking water. Tyrosine. Let me just say this. Again, my only subtle note that I might want to do when I create my own lecture is make sure that these respect what we talked about earlier. Make sure that this is O- and then is NH4+. We're missing that here. We know we're supposed to do that, and for sake of easiness in ChemDraw, we might have not done it when we were creating the slides, but we might want to maintain that idea throughout lecture. Let's make sure I check some learning objectives. So what have we done? Well, let's go back and just adjust this learning page a little bit, because I do think that what he's not done a great job of showing is this part. So I'm going to take that out because he hasn't really done a good job showing that. He's shown it in the 6-membered ring, and he's implied the mechanism. And granted, he hasn't shown it yet, which makes that learning objective something that's a little fuzzy, I would say. So I'm going to make that note. We might want to show that in class. Yes, I guess you could assume students can do it. He makes assume that the decarbox mech is clear. Is it? Or maybe it's in, let's just check for a second. Does he put it in the QTPs? Or I should check the answer keys to see if he shows it somewhere at some point. Without showing them on the stream. Let's just make sure. If you be my bodyguard, I can be your long lost pain. Nope, I don't see it. So that might be something we want to go over in class. Telling us why this PKA is so charged, because it has these extra ends donating electron density in. Which I'd be careful with those. Let's just go back for a second. Be careful with these PKAs, because he's implying that these PKAs are of the side chain, but over here they would be the PKA of the side chain if protonated. They're not protonated in this, so this PKA is a little bit confusing at first. Oh, thanks. I don't have to memorize this. Good. Good. We need to know the side chain ones, though. Nah, you don't. You don't. You can look these up. Or I would provide them on an exam. And they're super easy to look up. Just look at the Wikipedia article. Right, let me just prove that a second to myself. Right, if I look up lysine, if I go here, and okay, it's not as easy as I was hoping it would be. I'm sure there's a diagram that has a bunch of them. So let's just say amino acid pKa. And let's see a second. Lysine, lysine, lysine. There it is, pKa 10.67. So similar to their approximation of it. He's asking why are these lower than 5, thinking about the shape of an amino acid. Probably the this group's think. When you have this thing and you protonate it, you're creating a positive charge that's stabilizing the negative charge to the side. Right, which is what he's saying. It's about what's connected to it. How we're doing not how let's pause for a second. So what have we done so far in this class? Yep, great. Yep, great. Yep, great. Working on this, probably working on this. So we haven't done that yet. Alanine. Nope. Leucine. Leucine is most prevalent. A lot of carbon-based things. Yay! Now we're getting into these learning objectives. Multiple anions. That's him folding up a protein. Two acidic protons, low pHs. Most protonated as they can be. NH4 or ammonium. The carboxylic acid is its acid. Be careful worrying about the net charges. Well, I guess no. Be careful the net charges. That's going to be important for dealing with PL. As we move forward, let's talk about this graph really quick. The fraction of glycine with the blue line tells us it's in its protonated form, and the red line is it in its deprotonated form, and the black line is in its Zwitter ionic form, both a negative and a positive. As our pKa1, I'm not a... okay, so that's the... we're thinking about the equilibrium constant here, Ka1, Ka2, as we're going to different pHs, which would affect our equilibrium constant. How acidic or how basic the environment is would affect the equilibrium constant here. So as we go this way, we're going to more basic environments. As we're going this way, we're going to more acidic environments. And he's about to bring in, what the heck is this PL? of the Twitter ion. Interesting. Where are the graphs? Well, I guess it makes... Does it make sense? The halfway point is what you define as a pKa. 0.5. When it's 0.5 protonated, 0.5 not protonated, that's what you define as your pKa experimentally. When the pKa equals the pH. Going back to 202 here. PI. I call it PL, but it's PL. PI. No overall charge. No overall charge is important to say. So the PI is taking these two pKa's, adding them up, dividing by 2 gives you the PI. And so what's important about the Twitter ion is you need to know what's your +1 and what's your -1, because those are the pKa's you need to consider. And so before we go too much further in this, like, again, students do sometimes want, well, what's just the answer? And so if you go to this page, isoelectric points of amino acids, how to calculate the master organic chemist, right? If you don't want to have any understanding of chemistry, and also notice, did you know that this is actually from ChemDraw? This is a ChemDraw picture. How can I tell? The boundaries here are a very infamous ChemDraw, right? If I take this and I add a frame to it. Where is it? Add frame, and I want to do a rounded rectangle. See how that has that rounded rectangle that I just created? I know this guy loves ChemDraw because he's using ChemDraw to make these images. Anyways, the PI of an acidic amino acid is obtained by averaging the 2 most acidic pKa's. The PI of a basic amino acid is obtained by averaging the 2 least acidic pKa's. And with acidic or basic side chains that have 3 pKa's is how you do it. If they only have 2, it's a lot simpler. So that's the answer, but just... This is the Y. What he's talking about here is the Y. Your Zwitter ion is, the pKa's are between your Zwitter ion. So, okay. So learning objective 1, 2, 3, 5 are done, but 4 and 6 are a bit not covered yet. So he'll probably come back for that later. We'll see. But let's remind ourselves of this for midterm purposes. Well, wait a second. Wait a second. He's saying what is the most we have done for it. Which one? He's not asking for a percentage. He's just saying if you can calculate the PL, if you're at a pH lower than the PL, what does that mean? If you're at a PL higher than the PL, what does that necessarily mean? And well, actually, no. I should say this. It is still a little bit complicated because there is this area on the graph that is, there are some PLs that you still are not necessarily having more acidic or more basic. So we might need a little bit more help before we can do those. Or maybe that's a oversimplification, or at least that's what this graph is reminding us. It's a little bit of an oversimplification. Good. Okay, pKa, so what's our zwitterion? This one's our zwitterion here. So we take this pKa. Wait a second. Well, let's first make sure what I'm saying is right. So what are we dealing with here? We have a acidic amino acid, so we take the two most acidic pKa values. So it would be these two. What I was also trying to consider is the Y is that this second structure is the zwitterion. This is the positive, +1, -1, -2. So we take these two pKa's. So the PI is 2 or 3? Did I put that in here? I think it's 3. If I can do math, which I can't always do math, but I'm pretty sure it is. Yeah, it's 3. Okay, so let's think to ourselves, how generous can we be to our students? 1, definitely. 2, definitely. 3, definitely. I still don't think 4 is super well done, especially how confusing that other graph was, but in some ways maybe we have kind of done it. 5, we've done a little bit. 6, at any pH. I'm not 100% sure if we've done a good job at that. Let's look at some of the... So what class is this? This is class 8. Let's look at some of the QTPs for this. Na, na, na. Maybe instead of at any pH, at extreme pHs would be more appropriate looking at the QTPs. But let's keep looking. Okay, so this image was, I think, or this might have been an oversimplification. Is that an oversimplification? Feels like it's an oversimplification. The titration, what I'm worried about is that this line is straight, but when you look at the titration he shows later, it doesn't say straight for very long. Like, there's really not much of a straight line anywhere, and where there is the straightest line, it is a fairly small amount of base that changes the pH pretty drastically in the situation. So that's why I'm not crazy about this explanation. But I also have to, I think, come to terms with what is this? Oh, this is possibly pH. Okay, I'll be this drawing is a little bit unclear to me as to what they're talking about. Unless, well, let's see in another lecture. For now, how do I want to edit these? If at all. I should really leave it here. I think it's technically okay. And these two are so related. So I know it's I probably will get some flack from students for this, but I do think he's covered these things. Maybe not as well as we would like, but especially the fact that he showed us that titration curve is where I'm most comfortable with saying that. Well, he kind of has, especially here. Knowing that it's different for different side chains. But all right, let's see if he brings us at least through some examples. But for now, I'm pretty happy with that. So let's go back to our timestamps. Moving on. That class was a little bit more lecture-based, so less examples. So it took us a little bit longer, and we talked probably more than we should have. So let's say this one now starts at about 47. And remind myself, where am I on the schedule? So, okay, this is today's class, and we need to look at tomorrow's class, and those are our midterms. So all we have left is to consider these learning objectives, and then we can write another exam and teach in the class. Let's just pre-read the learning objectives together. Draw an arrow pushing mechanism for the reversible formation of an imine when an aldehyde or ketone is combined with a primary amine. Okay, cool, a new mechanism. Draw an arrow pushing mechanism for the reversible formation of an enamine when an aldehyde or ketone is combined with a secondary amine. Yep. So the key here is what do you remember? You know, primary, secondary carbons. Can you apply that here? Reductive amination. So wow, lots of new arrows. Structure synthesis. Wow. Cool. I love this. I'm pretty sure this is going to involve diastereomers. Or maybe not? Probably diastereomers, but we'll see. So it's basically, this class seems to be kind of going back to or we're going to walk away from macromolecules. It's like last class was a very macromolecule based class. So we'll say the math is not here. The logic is here for 4 and 6. But students might need some extra lecture help. So those are learning objectives I might want to keep an eye out for talking about in class tomorrow, as well as entropy, and that I don't need to talk about. Let's undo that. That I'll leave as something colored, but it's not something I'm going to cover in class. So let's undo all of this and say, this is not clear yet. This learning objective is not clear. So that we're going to want to make sure we talk about in class. And we're going to want to talk about that because it's there logically, but we might need some help on that. Oh, and I should review the LDA thing, right? Because that's something where he covers it. I can at least question it. Should I cover, or did he do good job? I think good job. What? And let's see what he doesn't get to, because then we can take some things out of this so students can be less worried about if I'm covering up to class 10. I'm covering up to what he covered in class 10. So what he covers by here we'll worry about. So 5.65, he's looking at phenylalanine. 2.18 plus 9.09, or I think he is 5.6, which is what he said. So great. Is he about to show it? PHE, so it's mostly similar with other ones. Nice. Nice. Remind yourself about this equation as we're going to go into it. Because this is what we were missing in the last class, right? If we look at how, well, I don't have it anymore, but I think if I go forward here, we'll have it. We'll go past the midterm. All right, what was kind of missing in the last class was the net charge, but most prevalent form. Yeah, I would say so. And really putting solid numbers on this we're kind of missing. But when you look at the Henderson-Hasselbalch equation, let's pull that back up, you get a percentage of the base, which we have to think to ourselves, what do we mean by percentage of base? We're thinking about the different forms of the amino acid, the charged form, the neutral form, the negative form. The cation form, the neutral form, the anionic form. Those are what are going to be defining these bases and acids, making sure we're choosing the right pKa, considering the pH, and we'll be able to give really cool numbers on these things. So, because the titration curve makes me feel a lot more comfortable. These curves I like better than that curve we saw in the last video. In last class, he shows this curve. He doesn't show a titration curve to introduce this idea. He showed something else. If you're just watching class 9, right? If you want to go back in the live stream and look at how I talked about class 8, there's one picture that made me a little bit like, I don't love this. It's a little bit confusing. Titration curves are a little bit better. Talking about titrations, the way a titration works is you increase your pH. So as time goes on, your pH is going up. One, two, 1, 2, 1, 2. What my attention is drawn to on these pictures over here is if the side chain is not charged or has things that are particularly acidic or basic, there should only be one time we kind of go straight up before going back over. And there are a couple of times where we kind of do it twice, like arginine, for example, goes up again. I think the most important thing to focus on, or what he'll hopefully focus on at some point, is when do you change the pKa? That's going to be key, if you have multiple pKa's to consider. But remind yourself in Wikipedia, the answer's there. The equation relates the pH of the weak acid to the numerical value of the acid dissociation constant Ka of the acid. So whatever you're defining as the acid in your equation is what the pKa is coming from. Oops. He's talking about these titration curves, looking at different points throughout it, what are important, what are not. What's really important is when they go straight up and down. Because what we're kind of doing is going back and picking up 5, 6, or 4, 5, or 4 and 6 from the previous lecture. Starting to get hungry. Log base 10 scale, 10 squared. Difference in 2. 10 would be if it was a difference of 1, 10 squared if it's a difference of 2, etc. 10 third. Haha, when it's equal to 1 to 1, child! 1 to 1! You're at the isoelectric point. That's the definition. Ah! That's the definition! Okay, let me pause for a second. I want to bring this up just real quick. This I feel more comfortable about. Notice how it's in, what I didn't like about the diagram he showed from the textbook is it makes it look like this is a straight line. It's not a straight line. There's a subtle, very small sloping down in both cases. That I'm more comfortable about seeing. And this is the log, or why we're seeing a log type curve. Or a log change in slope. This small slope change and then a big slope change. Base 10, base 100. Or not base, 10 versus 100. Now we're moving into this class. Interesting, making amino acids, right? We made an amino acid. That's an amino acid. How did we make it? Another way to make amino acids. It's going to be very important we know what amines are and what enamines are. And you're going to see, I think, when you see what an imine is, ooh, do you see what might happen here? If it's a double bond to something, what's probably happening here might tell you what's going on. And then what's the difference between that and an enamine versus imine? We'll see how those are applying here. Let's get rid of this. This no longer helps. He's asking, why is this a reduction? Why are we losing the, or I guess you're losing an O in some ways. You're adding an H. Less O's, more H is like a really simplistic way. Yeah, you can say it lost O. I think that's fair. I think it's about oxidation state is what he's trying to get them to say. The carbon is still -2 in some ways. Carbon, you know. Whatever's bringing in the hydride, that's what's doing the reducing, the H minus. That's what he's trying to say as the big point in this lecture. Remind students, so what is he saying? We're talking about reduction is adding electrons, but you're also considering the oxidation state, double bond to single bond, and other single bond is to a hydrogen. There's some resonance here. I think that he's trying to point out to students that if you made a boron carbon double bond, electrons could go onto nitrogen. Not particularly relevant to a learning objective, but nice review. Some induction, he's saying, because of the N being more electronegative. Let's pull this back up. All right, let's review what he's saying here. So this is an H- source. It's the nucleophile. He's saying it's less nucleophilic with the CN group. It must have a lower energy sigma CO or CO. Yep. The sigma BH is what's actually going to be the mechanism that he attacks with. It's lower in energy. N's more electronegative, pulling the electron density away from it. Carbon's positive, which then makes this less negative. Don't care about the sigma star. We're not doing this as an electrophile, which in a way is, I guess, what I was thinking about, where you can stabilize the anion through a double bond resonance structure. But not really a particular learning objective, so don't need to focus on this too much. That's how we're going to get an H-. That's where the H- comes from. That arrow's super important. That's what I was talking about a little bit. Stabilizing it, because he's thinking about this more as a p orbital, or overlapping with this p orbital, overlapping with this p orbital. He's shown resonance arrows, which he said was not ideal, but okay, so here's an important thing. We don't want it to attack the ketone. That's key. We don't want it to be as reactive or nucleophilic. We want it to attack the imine. For the imine to go first. And I'll say again, this is kind of an order of reagents thing. I would make my imine first, then I would add my source of reduction, but you can do them both at the same time. But order of addition is pretty important here. Oh, such a cool reaction. So again, over here we have the carboxylic acid. We bring in the amine, and then we reduce it to give this. Here we do a similar thing. We still bring in the amine in a similar kind of form, but instead of doing this reductive amination, we're bringing in a CN, which then we need to turn into a carboxylic acid. The CN is going to become the carboxylic acid. So we have the carboxylic acid, we just need the amine. Here we don't have the carboxylic acid or the amine, we need to bring in both. Strecker synthesis brings in both. Because remember, amino acid is a carboxylic acid and an amine. The first reductive amination, you already have the carboxylic acid. You just bring in the amine. This poor student's probably terrified who just got called out. Is this an oxidation or a reduction? I think he's saying for the second step. I don't think it is, right? Because it's still a C with 3. I don't think this is. Oxidation state didn't change. Look at him, just throw it out wrong. I mean, it's like, there's a point to this in some ways, but you gotta make sure your students know you. The point is, it's okay to be wrong. Three bonds to an electronegative, 3 bonds to an electronegative. Don't want to run it too acidic, don't want to run it too basic. Because of other things that are happening to the carbonyl, other things that are happening to... I wonder why a high pH would be bad. The reason we're low at a low pH is because your amine gets protonated and is no longer nucleophilic. And then why about the other one? Is it because the amine now attacks the carbonyl, maybe? Alright, so there's my answer, yep. My guess is that it becomes a more nucleophilic. Okay, great. Mechanisms. More S character. You goof. You are such a goof. What a goof. I will say this is a little confusing for students because, again, I don't know. In some ways, I kind of want to see this protonated because of how we started class. And we're in an acidic environment creating an anion, which I'm not crazy about, but I'll let it go for now. And I think this is a little bit of a... I mean, I guess I should always leave it to say that Dr. W is probably more right than me when it comes to these kind of things. But I think I have some argument here, at least to... Next time I see him and he has the mind space to talk about some of these things, you know, it could be fun to have some dialogue about some choices that he's making, which, again, he knows what he's doing. I'm just thinking about how I might teach this class a little differently in some ways. And maybe incorrectly, which I have to be careful of. Oh, well, let me say this, though. We're not... Yes, we do have a pH that is, quote-unquote, you know, somewhat acidic for this conditions that make it the most reactive. But primarily, you're doing this in NH3 with a ketone in... What would your solvent be? Maybe a polar solvent. Well, I wonder how we're making that magical pH, I guess. I'm not clear yet on this. Oh, that's why. His reason is no good leaving group. I also think you're a mean... Well, I'll leave it be. I'll leave him as being right. He's right. Agreed. Love it. Slightly acidic. Don't super protonate the nitrogen, but protonate the oxygen enough. Okay, great. So he does the first one and finishes up. Let's see. Let's take a quick break. So I'm going to go have dinner, and then we will come back and watch finally class 10. So I'm gonna just put a little note in here. Edit. Dinner time. Then class 10 soon, and that'll be at 4:25:40. So we are going to be back shortly to review class 10. We're kind of doing, like, not really a watch party of these classes, more of a commentary, and I'm just not sharing things in case students' names are coming up that I don't want to be broadcasting, but we'll be back shortly. I'm just gonna say this real quick. Oops. I'm gonna stop the stream for now and make a part 4 video where we go over class 10. I just don't want to pay the internet bill of streaming an empty screen. So we're gonna end the stream for now, but we'll be back on later tonight, finishing up this. So there's a recording of me reviewing the last class, me talking about what I think is testable or not testable on the next midterm. And then I'm going to take my own time, kind of shutting off all the streams just to be ready for class tomorrow, and then hopefully get some emails and discussion board figured out. If not tonight, tomorrow morning we'll figure all that out and get going. So anyways, I will be back in the office for emergency stuff, and we will go from there. So anyways,